Hi everyone. In previous lecture, I showed you that if you have a low-pass filter, by cascading this low-pass filter with a high-pass filter, as long as the cutoff frequency of your low-pass filter is greater than the cutoff frequency of your high-pass filter, then you ended up having a bandpass filter. And the frequencies between the cutoff frequency of low pass and high pass filter will be the range of frequency spectrum of your bandpass filter. But the problem is that you need to make sure that the cutoff frequency of low pass filter is greater than high pass filter. And this is for ideal situation. But if you have an actual low pass and high pass filter here, this is the Bode plot of a low pass filter, and this is going to be the Bode plot of a high pass filter. In order to find the cutoff frequencies, you know that you have to look at -3 decibel, assuming the maximum magnitude is equal to 0, then -3 decibel describe the cutoff frequency. So here I have the cutoff frequency of my low pass filter. So I'm going to call it as omega C2, and assuming that this is the maximum gain of my Bode plot for the high pass filter equal to 0 decibel, then at -3 decibel I have the cutoff frequency. So here I have omega C1. By cascading these two filters, I ended up having a bandpass filter. So the question is that what is going to be the cutoff frequency of the bandpass filter, which is the result of cascading these two filters? So I want to know if I choose this, how should I choose these cutoff frequencies in order to have the exact same cutoff frequency for my bandpass filter. So if I want to have the cutoff frequency of the bandpass filter as omega C1 and omega C2, which are respectively the cutoff frequency of my high pass and low pass filter, what is the constraint? The constraint is that they need to be widely separated. So if I can say that omega C2 here is much greater than omega C1, then I can assume that this omega C2 and omega C1 are the cutoff frequency of my bandpass filter. In order to see how it works, I would like to draw the circuit and analyze the circuit of a bandpass filter, which is the result of cascading a low pass and a high pass filter. So in order to make my bandpass filter, I would like to have a low pass filter with a gain equal to 1 or 0 decibel, cascaded with a high pass filter with a gain equal to 1 or 0 decibel. And then in order to add a desired gain, what I can do is that I can use an inverting amplifier at the end to provide my desired gain for this filter. So this is how I can make a bandpass filter by cascading these three components. Now, since you know the circuit for low pass, high pass, and inverting amplifier, I'm going to show you how the cascade will look like. So here I have the circuit for a low pass filter using an op-amp circuit. Now in this circuit, I need to have an input impedance resistor and a feedback resistor. In order to have a gain equal to 1, they should be exactly the same. So I'm going to call them both as RL. So I have to use exact same values for resistor. And let's assume that the value of my capacitor is CL. I'm using L to show that these are the parameter of my low pass filter. And then my input signal will be applied to the negative or inverting terminal of the op-amp. So here I have my input signal, which is Vi, and it is applied to the inverting terminal of the op-amp, and the non-inverting terminal of the op-amp is grounded. Now let's look at the circuit of the high-pass filter, which is going to be cascaded here. So again, in our high-pass filter, we have positive terminal grounded, and the negative terminal has an input impedance equal to R plus 1 over CS, or a series combination of a resistor and capacitor. So this time I'm going to call the resistor as RH to show that this is the parameter of high pass filter and this one as CH. Now again, in order to have a gain equal to 1 or 0 decibel, I need to choose exact same values for the resistor. So I'm going to use RH here as well to have a gain equal to 1. Now remember that the output of the op-amp in low pass filter, which is here, is going to be the input signal for the high pass filter. So it should be connected to the negative terminal of op-amp in high pass filter circuit. So what I have here is basically the signal at this point, which is now being fed to the high pass filter. At the end, in order to have a desired gain added to this band pass filter, I can use an inverting amplifier. An inverting amplifier does not change the frequency spectrum. It can pass any frequency. The only thing is that it will adjust the gain of the circuit. So I need to have something in this form. This is an inverting amplifier. The inverting amplifier has a gain equal to minus RF over RI. So RF is the feedback resistor, so what I have here, and RI is the input resistor, so what I have here. By choosing correct values for RF and RI, I can get an appropriate gain that I'm looking for. And finally, what I have at the end here is going to be my VO with respect to ground, or the signal here. Okay, so this is basically the circuit that I'm going to have in order to make a bandpass filter. Now let's look at the transfer function of this system. What we know is that when we are working with op-amp circuits, they don't have any loading effect on each other. So it means that if you have 3 circuits like this cascaded together, because they don't have any loading effect, then you can assume that the transfer function of this system is equal to the transfer function of the first part multiplied the transfer function of the second portion being cascaded and then multiplied by the third portion. In a normal circuit, you cannot make that assumption. You have to assemble everything together. You have to put everything together and solve the circuit and find the relationship between your output and input voltage. But in op-amp circuit, we don't have loading effect. That's why we can multiply the transfer function of cascaded component. But remember that if your low pass filter and high pass filter are passive filter, so if you're not making them with op-amp circuit, if you're making them with simple resistor, capacitor, and inductor, then if you cascade a low pass and high pass filter, you cannot assume that the transfer function of the overall circuit is the transfer function of low pass multiplied by the high pass filter. That's true only for op-amp circuit, which we know they don't have any loading effect. Okay, so because I know this fact, I can go forward with the bandpass filter transfer function. Before going forward, let's go back to the circuit and describe the cutoff frequencies of low pass and high pass filter. Let's assume that the cutoff frequency of my low pass filter is equal to X. And the cutoff frequency of my high pass filter is equal to Y. So if I know that these are the cutoff frequency, then I can describe the transfer function in this form. So my transfer function, which describes the output voltage to the input voltage, is equal to the transfer function of my low pass filter multiplied by the transfer function of my high pass filter multiplied by the transfer function of my inverting amplifier. Okay. What is the transfer function of my low pass filter? You know that the standard form for low pass filter transfer function is something in this form, minus omega c divided by s plus omega c. Here I'm assuming that the gain is equal to 1. And if it's a high pass filter, again with the assumption that the gain is equal to 1, it's going to be minus s divided by s plus omega c. Okay, so I'm gonna complete here what I have for my transfer function. The low pass filter transfer function has a cutoff frequency equal to x. So I'm gonna have x minus x divided by s plus x. The gain is equal to 1. The high pass filter has a cutoff frequency equal to y. So I'm gonna have minus s divided by s plus y. And finally, I have the transfer function of my inverting amplifier, which is simply minus RF divided by RI. Now let's multiply everything together and see what we are going to have for our transfer function. So this is going to be what we have for the transfer function of these cascaded circuit overall together. Now here, if you look at this transfer function, even without knowing the fact that by cascading a low pass and high pass filter with the constraint on their cutoff frequency, you can get a band pass filter. Even without knowing that, you can say here that this is a transfer function of a band pass filter because we have a second order polynomial in denominator, and in numerator we have a coefficient of s. If it was s squared plus a constant, then it was a band reject filter. But because we have s, it means that we are looking at a band pass filter. Now, according to the transfer function, I can find the cutoff frequencies of the transfer function. So if I look at this transfer function, I know that my center frequency, or omega naught squared, is equal to x multiplied by y, and my bandwidth, which is here, is equal to x plus y. So here I have omega naught squared, and here I have my bandwidth. Now I know that omega naught squared is also equal to the result of multiplying that omega c1 by omega c2, in which omega c1 and omega c2 are the cutoff frequencies of my band pass filter. So omega c1 and omega c2 are the cutoff frequency of the band pass filter, and don't forget that x is the cutoff frequency of my low pass filter, and y is the cutoff frequency of my high pass filter. And then beta is also equal to this greater cutoff frequency minus the smaller one. These are equations that I know they are true for every band pass filter. Now, looking at these two equations, the first one is basically telling me that x and y can be same as omega c1 and omega c2, but the second equation is not going to be correct because it's telling me that x plus y is equal to omega c2 minus omega c1. So here you can see that it's normally you don't have exact same cutoff frequency for your band pass filter as the cutoff frequency of the low pass and the cutoff frequency of the high pass. But if you follow one specific constraint, and the constraint is that your x is much greater than y. So if you choose the cutoff frequency of your low pass filter, which is x, to be much greater than the cutoff frequency of your high pass filter, then what will happen is that you can say that x plus y is similar to x minus y. Why I can make this assumption? Because I'm thinking about y being much smaller than x. So then, realistically, x plus y or minus y is not going to be different. Because let's assume that I'm choosing my x to be 1000. So the cutoff frequency of my low-pass filter is 1000. And I'm choosing my y to be, for example, just 2. Then what will happen is that, now you can see that this constraint is correct. So my x is much greater than my y. And here you can see, if I add them together, I have 1002. And if I subtract them, I have 998. These are very close that I can assume they are exactly equal. So then I can replace this x plus y by x minus y, and then according to the equation I have here, x multiplied by y is same as omega c1 multiplied by omega c2, and x minus y is same as omega c2 minus omega c1. Okay, so now I can make the conclusion here that in this scenario, if I have this constraint correct, then what will happen is that I can assume that omega c2, or the greater cutoff frequency, is equal to the cutoff frequency of my low pass filter, and omega c1, which is my smaller cutoff frequency for the band pass filter, is equal to y, which is the cutoff frequency of my high pass filter. Otherwise, you cannot make this assumption, and you have to solve these two equations to find your cutoff frequencies.